This network reads your handwriting. This one finds a friend's face in a photo. This one beat one of the best Go players alive. Nobody wrote the rules for any of them. No programmer typed, if it has a loop on top, it's a 9. Instead, these systems were shown thousands of examples, and they worked out the rules themselves. They learned. But what does it actually mean for a machine to learn? Today we'll open one up and watch, step by step, how a neural network teaches itself. Start with a task that sounds trivial. Look at an image and say which digit it is. 0 through 9. For you, it's instant, but try to write the rules. What exactly makes a 7 a 7? A line on top, a diagonal down? Fine, but what about a 7 with a little slash? A messy one? A child's scrawl? Every rule you write, some real 7 breaks it. The patterns are too fuzzy, too varied to pin down in code, so we flip the whole approach. Instead of programming the rules, we build a system that can adjust itself, and we let examples shape it. That system is a neural network. At its heart is something tiny and simple, an artificial neuron. Strip away the mystery, and it's just a little calculator. It takes some numbers in. For our digit, those are the brightnesses of the pixels, each one a number from 0 to 1. Every input gets a weight, a number saying how much that input matters to this neuron. Multiply each input by its weight. Add them all up, then add one more number, the bias, that shifts the result up or down. Finally, squash that sum into a clean range, say 0 to 1, through a simple curve. That output is the neuron's activation, how strongly it fired. And that's the whole neuron. Inputs, weights, a sum, a squash, almost insultingly simple. Why squash at all? Because without that curve, stacking layers would just collapse back into a single straight transformation. The nonlinearity is what lets the network bend and learn shapes far richer than a line. The power isn't in one neuron. It's in wiring up thousands of them and in the weights. Stack neurons into a column, a layer, then stack layers, each one feeding the next. That's the network. On the left, the input layer, 1 neuron per pixel. On the right, the output layer, 10 neurons, 1 for each possible digit. In between sit hidden layers. Every neuron connects to every neuron in the next layer, and each connection carries a weight. Feed in a picture, and a wave of activations flows left to right. The pixels light up the first layer, which lights up the next and the next. At the end, the 10 output neurons glow with different strengths. The brightest one is the network's answer. The hope is that the hidden layers learn to spot meaningful pieces. Little edges first, then loops and lines, then whole digits. Simple features combining into complex ones, layer by layer. Early layers tend to catch the smallest patterns, a stroke here, an edge there. Deeper layers glue those into loops and corners, and finally whole digits, crude parts becoming meaningful wholes. And every one of those thousands of connections has a weight. Together, those weights are the network's knowledge. So here's the real question. A network like this can have tens of thousands of weights. The big ones, billions. Set them at random, and the network is useless. Shown a 3, it might blurt out a confident 8. Learning means finding values for all those weights that make the network right, across thousands of examples at once. You can't possibly set them by hand. There are far too many, and they interact in tangled ways. We need a process that tunes millions of knobs automatically toward less wrong. That is the heart of the whole thing. To improve, the network first has to measure how badly it's doing. We call that the cost. Show it a labeled image, say a 3, look at the 10 outputs. We wanted the 3 neuron at 1 and all the rest at 0. Take the difference between what we got and what we wanted, square it, and add it all up. A big number means a bad answer, a small number, a good one. Average that over thousands of examples, and you get a single number. How wrong is this network overall? Now learning has a crisp goal. Make that one number as small as you possibly can. Here's the mental leap. Think of the cost as a function of the weights. Nudge a weight and the cost shifts. We want the weights that sit at the very bottom. So picture the cost as a landscape. Every possible setting of the weights is a spot on the ground, and its height is how wrong the network is there. Learning becomes one thing: find the lowest valley. Picture the simplest version, just one weight. Plot the cost against it, and you get a curve with hills and valleys. You're standing somewhere on that curve, and you want the lowest point, but you can't see the whole landscape. You can only feel the slope right under your feet. So you do the obvious thing: look at which way is downhill and take a small step that way. Then feel the slope again and step again. Roll downhill over and over, and you settle into a valley. That simple idea has a name: gradient descent. The slope tells you two things at once: which direction lowers the cost and how steep it is, which hints how big a step to take. Now scale it up, not one weight but thousands. The cost is no longer a curve, it's a surface in a space of thousands of dimensions, impossible to picture. But the math doesn't care. At any point, there's still one direction that goes downhill fastest. That direction has a name: the gradient. Gradient descent is just this. Find the downhill direction, take a small step, repeat. Each step nudges every weight a little, and the whole network gets slightly less wrong. How big a step? That's the learning rate. Too big and you overshoot, bouncing past the valley. Too small and you crawl forever. Getting it right is part science, part art. And it isn't flawless. A landscape this wild has many valleys, and you might settle in one that isn't the deepest. Remarkably, in these vast spaces, the valley you land in is usually good enough. But one step changes thousands of weights at once. How does the network know which weights to blame for the error and which way to nudge each one? That's the job of backpropagation. The idea is to assign blame backwards. Start at the output. The 3 neuron should have been brighter, so we want the weights feeding it to push it up next time. But those weights depend on the neurons before them. So the signal, "you should have been brighter," flows backward, one layer at a time. Each layer hands a share of the blame to the layer behind it, in proportion to how much it contributed to the mistake. By the time the signal reaches the front, every single weight has a number attached. Nudge me this way by this much to reduce the error. That whole collection of nudges is the gradient. Backpropagation is simply how we compute it efficiently. Under the hood, it's just the chain rule from calculus, applied over and over. But the picture is what matters: error, flowing backward, telling every weight exactly how to change. Now put it all together into a loop. This is training. Show the network a batch of examples. Let activations flow forward and read the outputs. Measure the cost, how wrong it was. Run backprop to get the gradient, the direction of blame. Take one small step downhill, nudge every weight. The network is now a hair less wrong. Then do it again, and again. Thousands, even millions of times across the whole dataset. Slowly, the random mess of weights organizes itself. The cost falls. The network starts getting digits right, not because we told it the rules, but because it found them. One full pass through the data is called an epoch, and it takes many. But beware, train too long, and the network starts memorizing the examples instead of learning the pattern. That's called overfitting, and fighting it is half the craft. Let's watch it happen on something we can actually see. 2 kinds of dots, scattered on a plane, and a network learning to separate them. At the start, with random weights, its dividing line is nonsense, slicing straight through both groups. Step by step, the boundary bends and curves, settling until it cleanly wraps one group apart from the other. No one drew that shape. Gradient descent found it. That's learning made visible, a surface slowly molding itself to the data. And nothing there was special to dots on a plane. Turn anything into numbers, and the very same machinery grinds away at it. This idea is older than you might guess. The first artificial neuron dates back to the 1940s, and the first one that could learn, to the 1950s. But for decades it underwhelmed, starved of data and computing power. This single idea, measure the error and follow the gradient down, is the engine under almost all of modern AI. Swap digit images for photographs, and you get systems that recognize faces and tumors. Swap them for sound, and you get speech recognition. Swap them for text, scale the network to billions of weights, and you get the large language models writing and answering today. Same engine, just more knobs and more data. What changed was scale. Around 2012, with enormous datasets and fast graphics chips, deep networks suddenly leapt past everything else, and the modern AI era began. But it's worth knowing the limits. A network only learns what's in its examples, biases and blind spots included. And it can't really explain itself. We can watch the weights, but why it decided something stays largely a black box. It isn't magic, and it isn't understanding in the human sense. It's optimization, staggeringly effective at staggering scale. So step back and look at what just happened. We didn't program intelligence. We built a flexible system, gave it a way to measure its mistakes, and let it roll downhill. No rules for what a 7 looks like. Just examples, an error to minimize, and millions of tiny corrections. A neural network isn't written. It's trained, shaped by its own mistakes, the same way we learn most things that matter. Simple parts, a clear goal, and the patience to be a little less wrong, over and over. That is how a machine learns.